Okay, the first step in solving this problem is to look at the points A and B. Here are points A and B, where the capacitor is connected between the output point A and the ground point B. And we need to find the Thevenin equivalent circuit for the resistor network that's connected between VCC with respect to the VCC and ground with respect to the points A and B. Okay, so we've done this before. In this case, we have 1600 ohms. Here's the point A, and then here's 800 ohms, which is connected across point B. And we want to find the Thevenin equivalent circuit with that being 5 volts. Okay. All right, so we've done that before. We know that the equivalent resistance, R Thevenin, is 1600 in parallel with 800 ohms. And when you work that calculation out, you get 533.3 ohms. And then the voltage, V Thevenin, is a voltage divider between 800 and 1600. So you get 5 times 800 divided by 800 plus 1600, which gives you 1.667 volts. Okay. So that lets us move to point A, where we have, or part A, where Vn is an ideal low. If Vn is an ideal low, then Rp should be switched on. The on resistance is 200 ohms. And then we connect the capacitor and then the Thevenin equivalent circuit. Okay, so that's the equivalent circuit we need for part A. Okay, in part B, we're assuming that this low has been applied and we leave it for a long time, and we're wondering what the output voltage here goes to. So remember, what you do is you do an open circuit for the capacitor, and so what that leaves us with is essentially a calculation for V out. V out's going to be this current, I, be 5 volts minus 200 times I. Okay, and we can find I by looking at the voltage across the resistor combination. So it would be 5 minus 1.667 divided by 200 plus 533, so 733.33 ohms. And when you do this calculation, you get V out to be 4.09 volts. Okay, so that moves us to part C. In part C, Vn is an ideal high. Okay, so that makes the equivalent circuit, this is still 5 volts, but this is now a really large resistance, so it's effectively out of the circuit. We have the N channel modeled by a 100 ohm resistor. Then we have our capacitor hooked up across the output. And then we have our Thevenin equivalent circuit. Okay, so there's that equivalent circuit. And what we're looking for is the steady state output across the capacitor. So you treat the capacitor as an open and you look at the voltage. So that would be the voltage across the 100 ohm resistor. So you can get that by a voltage divider. The steady state output voltage for a low is going to be 100 times 1.667 divided by the series resistance, which is 633.3 ohms. So you do that calculation, and I get that to be 0.26 volts. Okay, so that's part D. In part E, we want to look at the rise time and the fall time. Okay, so if we start with the rise, we're going to end up in a high state. Okay, so we would use the equivalent circuit that ends up in a high state. So that'd be the part A equivalent circuit. And what we're using to approximate the rise time is just the time constant of the circuit. Okay, so the time constant, this is just a simple RC circuit. So it'd be R equivalent times C. And if you go back to part A, we're taking the equivalent resistance with respect to the capacitor, turning off the sources. Okay, so if I cut this, I could explain it a little better. All right. So what we're talking about doing is shorting the voltage supply, shorting this voltage supply, opening the capacitor, and looking at the equivalent resistance seen by this terminal pair. Okay, that equivalent resistance is 200 in parallel with 533.3 ohms. So you do that calculation and you get the time constant tau is equal to R equivalent times C, and when I plug it all in, I get 10.91 nanoseconds for the rise time. Okay, fall time is a similar calculation. Only this time we want to use the circuit when it's in the low state because the output voltage would have fallen down to the low state. Okay, and so you'd use the second equivalent circuit for that. Okay, skipping some of the steps. The equivalent circuit in that case is going to be the 100 ohm resistor in parallel with 533.3. So you plug that in. We know the capacitance value is 75 picofarads, and I calculate the fall time to be about 6.3 nanoseconds. Okay, so that's the solution to the sixth problem.